the recording. Okay, the recording is started. So let me turn the mic on. Do you have any questions before I start? I think everything is fine, meaning that we are on schedule, even if, as you know, with this lecture, we are getting to the midway of this course of these 24 hours. We are on schedule, as I said, and the videos are uploaded. So I think you have everything you need. You also have on the web page the calendar of exams. And once again, if you have any questions, please let me know. Last Monday, we discussed the climate models and how they are structured. I used a PowerPoint to explain to you that these models work by discretizing the volume of the Earth system, which we call the control volume, the volume over which we apply our equations. These models discretize the volume into elementary volumes, and there are millions of these elementary volumes over which, over each one of them, a set of equations is applied to describe the unknowns that typically are the climatic variables we are interested in, the climatic variables we are interested to predict. And these elementary volumes exchange matter between them, exchange energy, exchange water, exchange other matters, so that the resolution of this system of millions of equations must be searched with by contemporarily working on all of these equations. So they cannot solve individually, they need to be solved all together. And therefore, I said, you understand the complexity of these models, also in terms of computing requirements. And this is why only a few computing centers in the world can run these models. And then we discussed the input. And in particular, we discussed the CO2 input, the input in terms of CO2 emissions and concentrations. And we discussed how these concentration data, CO2 concentration data, are delivered into models. Basically, what we do is to make a prediction of what we believe the CO2 emissions by humans will be, by human society, and also by natural processes. We make a prediction of these emissions, which turn into prediction of concentrations, and we use this data to fit climate models. Let me open, I want to give more details on these emission scenarios. Let me open a Google window, and let's search for RCP, which is the acronym that we use for identifying these scenarios, so RCP scenarios. And you see here a graph that is similar to what I showed you last time. And this graph depicts the progress of different scenarios depending on assumptions that we make on the evolution of the human activity, evolution of human society, which will determine, of course, the emissions, the associated emissions. And I said that there is a business as usual scenario, which is the most pessimistic, which is identified here with the acronym RCP 8.5. And there are other emission scenarios that correspond to the application of several policies, of assigned policies for reducing, mitigating our emissions. These pathways are computed without a standardization at the global level of the socioeconomic development. And therefore, recently, starting from the 5th report of IPCC, they started to associate to these emission scenarios a version that is standardized. And they are identified with the acronym SSP, which stands for shared socioeconomic pathways. And these are very similar. So if you look at the picture, it's very similar. And also the acronym is similar. So 8.5 is, again, the business as usual. And if you compare these scenarios with the RCPs, you will see slight differences. Slight differences because, as I said, with the SSP, what is done is a standardization at the global level of the computation of the socioeconomic component, of the effect of the climate policies. Basically, with the RCP, they are computed individually in each country with similar procedures, which are not anyway standardized. With the SSP, they standardize these emissions. From a practical point of view, and for your knowledge, there is no much difference. I'm delivering this information because I don't want that you get confused if you see two different acronyms that indicate a very similar prediction. The only difference is that the SSPs are an evolution, are an addition with respect to the RCPs, and this evolution is obtained through standardization at the global level of the methods for computing the effect of assigned socioeconomic hypothesis. I go back to the PowerPoint in order to discuss now the time resolution. We discussed already the spatial resolution. I said that modern models, most of the available models which you can find, their output on the web, work with a resolution of 25 by 25 kilometers, which is something like 600 square kilometers. And I mentioned that the new generation of models that are becoming available now work at a resolution of 5 by 5, which means 25 square kilometers. I'm talking about spatial resolution. And I mentioned also that there is currently work undergoing and to generate predictions for Italy at 3 by 3 kilometers resolution, which means 9 square kilometers. You understand? It's a resolution that is becoming very fine, and we want to reach this fine resolution because we want to describe convective processes with the most possible, the most refined details. And the convective processes are those originating, for instance, the thunderstorms, which we experience in our climate in summer, typically. These are very short in time phenomena and very local. You know, these thunderstorms have an extension in terms of surface that is covered that is very limited. Sometimes it's just a few square kilometers, maybe less than that. So in order to describe these processes, which are very localized, very local, we need a higher resolution in space. But what about the resolution in time? As you can understand, these models are applied by solving differential equations. We know why. We studied why we need differential equations. And these differential equations describe changes in variable each time step. And in order to solve them numerically, basically, in practice, we estimated this difference. So variable temperature, we estimate the difference in temperature from one day to the next day. So, and for variables like rainfall, for variables that need a finer in time description, we can use a time resolution that is lower than one day. For instance, if I want to describe these thunderstorms that typically last like 5 minutes, you understand that you need a resolution that is comparable, at least comparable to the duration of the process I want to describe. or maybe lower. This is because if I want to describe something that is very local, the space or time, I need to work with my equations, with my model, at the same local scale, at least, or final. There is also to say that there are approximations in the numerical analysis, in the numerical computation of these equations, and these approximations become lower and lower as we decrease the resolution, both spatial and temporal resolution. So in terms of time, usually we work most of the GCM, so frequently GCMs work at a time step that is typically 30 minutes. So it's quite a final solution. But still, you understand that if you want to describe a process that lasts for 5 minutes, you need to refine this time solution. You need to go further than 30 minutes. I apologize, I forgot to turn the phone off. Give me 1 second. Okay. Okay, so you mean, you understand that also the time resolution plays an essential role in terms of computational requirements. And also, you may understand through a logical reasoning, the limitation of a final solution, meaning that it is quite understandable, quite obvious that if you model something at large scale, large in space, large in time, the error that you make is lower. Uncertainty is mitigated with respect to modeling something at very local scale. Because local scale means additional detail, means that you need local information. If you want to describe something that is rapidly varying in the space of like 200 meters, you need information, input information in terms of land use, in terms of forcing, that is given at a comparable scale. So you need more data. This means that if you describe at a very local scale, the uncertainty is larger. So this is why sometimes climate models are used, even if they run at local scale, they are used in statistical terms. What I mean to say, instead of using the local variable of a prediction, we use the statistic of a prediction, because in this way we minimize uncertainty. And this is why sometimes, instead of using climate models for predicting climate variables in the year 2050, we prefer to describe the average over a window which may be 2050, 2050, instead of predicting the climate variable for the year 2050, we prefer to describe the average over the window, for instance, 2045, 2055. So we average over 10 years, because this is also adhering to the definition of climate. You may remember, if we go with a specific reference to 1 year, this is weather. If we go to average over 10 years or more, then we get into the domain of climate. What I mean to say, we shouldn't compare the output of a climate model with what we observed in only 1 year. So for instance, climate models may be run also to reconstruct past climate. So I can simulate global temperature in 1950, which was also observed. I shouldn't compare the prediction given by a climate model for 1 single year. Better to compare statistics. And keep in mind that in order to reach the desired scales, spatial and temporal scale, sometimes the output from coarser models, so the output from models working at a larger scale, are downscaled. What does the term downscaling means? It means that we take the output from a model at large scale and with additional models, with additional post-processing, we downscale the climate models. For instance, by using statistical approaches. So when you hear the term downscaling from climate models, it means precisely this operation of bringing an output at large scale to a final spatial and temporal resolution. It is important that you get familiar with the terminology because this is something that is important in order to understand the progress in science, to understand science itself. And sometimes these downscaling models are called weather generators. You understand why? Because if I start from a statistic over 10 years and I generate realization of the same variable over one day, what I obtain is generation of weather. If you have any question for me, you can discuss with me and avoid to speak together, the two of you. I'm sorry, but as I mentioned to you, I really can listen very well what you're saying. And even if it doesn't look that I can listen, you know, this room is very good. And if there is only a small background noise, it's a problem for me because I can really listen to what you say. So if you have to discuss something, it's no problem. You can leave the room and come back later. I apologize for this. Okay, and now I want to give you an example which clarifies our climate model is structured and what does scale means. The example, I think it is very significant. It's a climate model that we can write with only one equation describing the whole Earth system as an homogeneous entity. So we don't have to discretize the Earth system into millions of control volumes. We have just one volume, which means that the number of equations is drastically reduced. In fact, in this case, I get only one equation. Okay? So it's one equation because it's only one unknown. I don't need a state variable, and the control volume is just given by one volume. And the purpose of this model, which is an historical model, it was derived like, I don't remember the year, but I think it's like 200 years ago. It's a model that makes a balance of the energy in terms of heat that reaches the Earth and derives the temperature. So let's look at this equation. On the left-hand side, we have the incoming solar radiation from the sun. S is precisely the incoming solar radiation per unit area, and we know the value. The value is about 1,367 watt per square meter. So it is a solar radiation per unit surface of the Earth. So if you multiply the solar radiation per unit surface S by the surface of the Earth that is exposed to the solar radiation, you obtain the total incoming solar radiation. The total incoming solar radiation is given by, the total surface of the Earth that is exposed to solar radiation is given by pi times the radius of the Earth to the power of 2. So again, the solar radiation is hitting half of the Earth, as you understand, half of the Earth that during the day that is getting the direct solar radiation, and the surface projected on the perpendicular plane, perpendicular to the solar radiation itself, the surface is given by the product of pi times the square of the Earth r to the power of 2. Because the radius of the Earth, the power of 2 times pi, gives the area of the circle. And the Earth projected in this perpendicular plane is like a circle, okay? Now, actually, not all the solar radiation is retained by the Earth, because we have to consider the albedo. The albedo is the fraction of the solar radiation that is reflected back into the space. And the albedo of the Earth is about 0.3. Keep in mind that a black body has an albedo of 0, a white body has an albedo that is close to 1, and we know that the albedo, the overall albedo of the Earth is about 0.3. So if I multiply 1 minus A, 0.7, times S, incoming solar radiation, times the exposed surface of the Earth, pi times the radius of the Earth to the power of 2, we get on the left-hand side the incoming total solar radiation. Incoming meaning that is absorbed by the Earth. Now, at the right-hand side, we need to compute the heat that is emitted by the Earth. Once that the Earth was heated up by the solar radiation, there is a fraction of this heat that is emitted back to the space. And this can be computed by the surface of the sphere, the Earth sphere, which is given by 4 times pi times the radius lowercase r to the power of 2, first 3 factors on the right-hand side. And then we have to multiply by epsilon, which is the effective emissivity of the Earth. Again, if the Earth was a black body, emissivity would be 0. And we know that the effective emissivity of Earth is about 0.61. And then we have the Stefan Boltzmann constant, which was derived by numerical experiments. And then there is the temperature to the power of 4. You see that in this equation, we know everything. And we can derive T, which is the average temperature of Earth. How can T be derived? Before moving to the next slide, I just want to make a summary. So we have an equilibrium equation here, an equilibrium equation in terms of heat. Heat that is incoming by the sun, and the heat that is emitted back by the Earth. And we know everything. As I said, we know S because we made experiments. We know the Stefan Boltzmann constant, and we know the Earth radius. We know pi, of course. The only thing that we don't know is temperature. So temperature can be derived with a simple equation, and the result is in Kelvin degrees, because the Stefan Boltzmann constant, I go back 1 second, is expressed in terms of Kelvin units, Kelvin degrees. I just want to remind you that Kelvin degrees is you can obtain the Celsius degrees by subtracting from the Kelvin degrees the quantity of the absolute zero, which is 273. So again, degree centigrade is equal to degree Kelvin minus 273. So you get the result in degree Kelvin, and the result in degree Kelvin is 288. You can easily try with Excel, which means an average temperature of Earth that is 15 degrees, which is correct. It is correct. So this equation is, I think, a nice example because it illustrates in a very simple way how a climate model can run. Of course, if you want to describe other variables other than temperature, you need to add additional equations. And with a relatively simple set of additional equations, you could describe the average rainfall, for instance, at the annual scale over the Earth. Of course, you need estimates of evaporation, because if you want to make a balance of the mass of water, mass balance, remember, it's a conservation law of water, you need an estimate of evaporation, and then with a simple estimate of global evaporation, you can derive with a very simple equation. Of course, evaporation depends on temperature. With a very simple additional equation, you can derive the value of the annual global rainfall. By the way, annual rainfall at the global level is about 1 meter. Okay, so this is interesting to know. The orders of magnitude are interesting to know. And it's, again, the annual rainfall, which means the total precipitation, better term, total precipitation in terms of depth of the water column in 1 year, averaged over the globe, is about 1 meter. And by the way, the annual rainfall in Bologna is about 800 millimeters, so it's comparable. And to give you an idea, in the south of Italy, annual rainfall is about 600 millimeters. In the Alps, you may reach like 2 meters. At the very local level, you may reach extremes of 2 meters per year. So I think, as I said, these equations are a nice example because they allow you to understand how our model may run, and it's very simple. In order to get a representation prediction at local scale, you just have to apply the same equations at the local level, with the problem that the conservation law depend on the fluxes through the boundary. And therefore, any equation depends on the corresponding equations in the neighboring control volumes, which is the complication. It's a computational complication. Okay. Second thing that is interesting to know is that, as you may see, let's look back at the equation. What is determining temperature on Earth at the very large scale? It is determined by the incoming solar radiation. It is determined by the albedo, and it is determined by emissivity. You may say, where is the impact of CO2 emissions here? The impact is that emissivity, part of the heat that is emitted back by the Earth, is trapped into the atmosphere. So there is a decrease of the emissivity. If there is a decrease of the emissivity, because, as I said, part of the heat is trapped by the atmosphere, part of the heat that is emitted back by the Earth is trapped by the atmosphere. If you decrease the emissivity in this equation, you understand that in order to keep the equilibrium, you have to increase temperature. Fortunately, temperature is raised at the power of 4, which means that you don't need an equivalent change in temperature to compensate for a change in emissivity. It's not linear. The power of 4 helps us, because even a small increase of temperature compensates a large decrease of emissivity. But still, we need a compensation. And you can understand why then temperature increases with the greenhouse effect. And you can understand why we don't have to expect an increase in temperature of millions of degrees. Actually, global warming is 1.3, as we mentioned. Because in this equation gives to you the idea of how the process works. So for this reason, I think it is interesting. You may look over the web at this website, or you may look for this in Google, for this acronym CMIP, and let's add climate. Sorry, you see that I have already an entry here, CMIP climate model. Okay, and you see the first link. It's a link that goes to the World Climate Research Program, and precisely to a project that is called Coupled Model Intercomparison Project. What is this project? This project compares the output from different climate models. And you see here, this helps evaluate climate models, leads to improvements in the model simulation, and provides a better understanding of past, present, and future climates. Here there is a video, a small video that explains, a short video that explains the aim of the project. What they do, given that these models differ each other, they differ not only for the different emissions. I leave the video moving forward. I'm not sure I can, let me stop it. I'm not sure I can, because I am recording and putting on YouTube. I don't think I can put on YouTube a recording from a YouTube video. So let's stop it. And you can watch it yourself if you wish. And what they do, as I said, they test different models, which don't differ only for the emissions, for the input data. They differ also for the structure, for the equations that they consider, for the different assumptions, hypotheses, and they produce a different output, even for the same location, even for the global temperature. And they compare each model. And there is also another purpose. It's not only comparison. Is to produce what they call an ensemble of simulation. We will get back to this in a moment. Why it is useful, the ensemble? Clearly, it is useful because it gives to you an idea of the uncertainty that is associated to different hypotheses, assumptions, using different models. If we know that a model is not perfect, a way to quantify the uncertainty is to compare with other models. Another way is to compare with observations. But in order to get feedback on the impact, on the effect, on the uncertainty induced by different, as I said, assumptions, different equations, different parameters, a different way of applying models, this ensemble gives an envelope of predictions, which gives an idea of the associated uncertainties. And this is a way to quantify uncertainty of climate models. This is the way IPCC usually presents the results. IPCC, you know, is the Intergovernmental Panel on Climate Change. It's a scientific body that aims, of the United Nations, that aims to analyze climate change, make predictions, and estimate the future impacts. And this is how they assess uncertainty. In some of the cases, they may give priority to some models. And basically, they may say, okay, this is the ensemble of all models, but they may identify the ensemble of the sub-models they trust more, because they give different priorities. Let me go back to the PowerPoint, because I'm close here to, after some slides on the emission scenarios that we already discussed, there are slides dedicated to uncertainty. And let me show you. This is, for instance, the ensemble reconstruction of past climate, past global temperature, in terms of anomalies, differences from the mean, that are obtained by using three models, and three very good models, and they are sorry, two models plus the observations, okay, because this is a reconstruction. So the green line is observations, And then you see two models. First, you see that indeed there is uncertainty in these two models. And by looking at the differences at the envelope, at the interval between the blue and the red line, you can get an estimate of uncertainty. This is still not really encompassing the green line. A good estimate of uncertainty should encompass the observations. It's not encompassing because this is not really an ensemble, it's just models. But if you go further, this is an ensemble of more models, and you see about 10 of them. And we don't see the observations here, but you see that now the envelope is more substantial. And what you see here is that when you look at the past, uncertainty is reduced. When you look at the future, then uncertainty, so differences between models, is larger. And this is to be expected. It's perfectly understandable. I mean, it's easier to predict the past than to predict the future. And there is a saying that says making prediction is particularly difficult, and in particular when prediction refers to the future. And here the logical explanation is that these models are to some extent, in some way, calibrated, optimized to reproduce the past. So if we see that a model is not good in reproducing the past, we adjust the model. And also there is to say that the input data for the past are known. For the future, we need to predict them. So in the past, we know the CO2 concentration of the atmosphere. It was measured. In the future, we have to make assumptions. We have to predict it. And therefore, there is more uncertainty. So this way of presenting the results is typical in a set of climate models. Actually, I mentioned briefly a few seconds ago that another way of estimating uncertainty is by comparing models with observations. So you reproduce the past climate, you look at the errors, and you may assume that the same errors are repeated into the future. First of all, let's consider mechanism. If you consider an ensemble of different models, as I said, you estimate the uncertainty given by some things. For instance, different assumptions, different equations, different parameters. Okay, this is called model uncertainty. But you understand that it's not the total uncertainty, because there is more than different assumptions, different. So let's, for instance, assume that all models are wrong. If they are all wrong, the envelope of their prediction doesn't include the true value, because all models are wrong. So it means that besides model variability, model-to-model variability, we may need to consider some more. For instance, chaos. For instance, the fact that all of the models don't reproduce the climate perfectly. So there is some more that has to be added, some joint common error. When instead you estimate uncertainty by comparing with observations, in principle, you include everything. You include model-to-model variability, whatever, and also some more. You include everything. When you make a difference between an observation and a prediction, it encompasses everything determining uncertainty. But there is the problem that you may not have observations, or there is the problem that climate models are not conceived for reproducing a specific observation. So this is why uncertainty in climate models is often represented just by looking at the ensemble of model predictions. But keep in mind that this is not the overall uncertainty. You have to be aware of that, because you have to take uncertainty into account. And even if you get a small envelope, it doesn't mean that the prediction is fully reliable. There might be uncertainties that are not taken into account by the ensemble. Okay? There are some slides here about uncertainty, and you see different types of uncertainty. So first of all, forcing uncertainty, meaning that I can make a mistake in my prediction of emissions, my prediction of CO2 concentration. And if the prediction of CO2 concentration is wrong, all models are wrong. So the ensemble doesn't include this. Unless I try the models with different emissions. But usually the models are run with reference to a specific scenario. So forcing uncertainty first, and the main source of error is in the CO2 concentration. Model uncertainty, which means that any model can be wrong, and uncertainty over initial conditions. These are the sources of uncertainty that are mentioned by the IPCC. Okay, and then the way is to use ensemble, the way the results are presented. And I already discussed the limitations of the ensemble simulation. Same thing for the other variables. Here I talked only about temperature, but the other variables, same thing, with some additional considerations. When you try to predict something, when you try to predict anything that is interesting to you, you have a clear perception that slowly varying processes, where with slow I mean slowly varying in time, slowly varying in space, are easier to predict. To predict something that is subjected to sudden changes in time or space is much more difficult. Clear. It is perfectly clear. Even persons. There are some persons that have a character that is to be predicted because it doesn't have spikes. Their behavior doesn't have spikes. Okay. There are persons whose behavior is maybe more difficult to predict because it's rapidly varying. What is the moral of the story? The moral of the story is that if your climatic variable is slowly varying, like temperature, temperature doesn't change much from 1 minute to the next one. Okay? It's easier to predict. So when you get an output from a climate model in terms of temperature, you can trust the climate model with more, let's say, more convincement, with more enthusiasm, let me say, with respect to a prediction of rainfall, because rainfall is rapidly varying, but not only rainfall, wind, prediction of wind, you understand? It's something that is rapidly varying in time and space. So keep this in mind. When you get a model predicting something, try to understand the variability. We talked about variability in the first lecture. If the variability is very pronounced, you have to evaluate uncertainty in a different way. Okay? And same reasoning for the very fine details. Temperature at the very local level, it's more difficult to predict. It is more difficult to predict temperature over the Alps than over the whole of Italy. Clearly, because over the Alps is much more variable. Over the whole of Italy, averaging reduces variability. When you go very local, in time and space, variability increases. As you can see, the concept of scales comes very frequently into my wording. So keep it in mind. Scales are extremely important in environmental modeling, including climate modeling. So scale of the prediction, spatial scale, temporal scale, they are extremely important. And the choice of the proper scale is extremely relevant for choosing the model, evaluating the prediction, evaluating uncertainty, whatever. What is a way to manage uncertainty? A way to manage uncertainty is through statistical analysis. And a branch of statistical analysis is stochastic. Stochastic means that the progress in time or space of a variable is analyzed. It's not only one value temperature over Italy, but it is progress of temperature over Italy for 100 years. And an alternative to the global climate models is represented by a statistical model, which starts not from the physically based equations, conservation laws, but it starts from statistical laws. I already made to you the example that I already mentioned to you that conservation laws can be approximated by empirical equations. And empirical equations typically are derived by analyzing data. Statistics does precisely the same thing. Empirical analysis of data and the derivation of empirical equations, with the advantage that in statistics, any derivation of empirical equation is driven by a very rigorous theory that makes sure that your assessment is unbiased, is objective and transparent. Okay, so statistics, I would say, is a bit more than an empirical approach. I know that some statisticians, if they listen to me saying statistics is empirism, they would like jump over their seats, because statistics is a little bit more than just empirical. It's not a mere fitting of data. There is a very rigorous theory behind. The drawback of statistics is that the rigor of the underlying theory makes the theory itself a little bit difficult to digest. But actually, the procedures are very simple. So in a way, don't forget that also statistical analysis is essential to analyze climate and to make predictions, to make climatic predictions. Also, the IPCC does some statistical interpretation of the results. I think I am okay with this discussion on climate models. So what is the moral of the story? The moral of the story is that we need predictions of future climate to make, to elaborate any mitigation or adaptation strategy, mitigation or adaptation of climate change, of course. We need prediction. We need what are called climate scenarios, future climate scenarios, corresponding to different levels of CO2 concentrations. And these scenarios can be derived at various scales. Scales are extremely important, spatial and temporal scales. These scenarios can be derived with several different models. A class of models is given by what we call physically based model, based on the law of physics. And typically they are based on conservation laws. Another class of models is given by the statistical models or stochastic models, because statistics applied for describing a variable in time, we call it stochastics. And usually, we need to deal with uncertainty, not usually, we need to deal with uncertainty. Uncertainty can be estimated through ensemble predictions, but don't forget that it's not enough. The overall uncertainty should be estimated by comparing predictions with observations. And this is not always possible, so this is why we often use ensembles, okay? Probably the way forward, but some climate scientists wouldn't agree with me, is the integration, combination of the two approaches, climate models plus stochastic models. By combining them by making a synthesis, it's not just a mere combination. It's not just obtaining one prediction from this model and one prediction from the stochastic model. It's not just another member of the ensemble. We need to make a synthesis. The results are to be put together. Okay, and this is probably the one possibility to further evolve, to further making our prediction representative of the future climate. At present, we have uncertainties, but it's not a big problem because even if there is uncertainty, we can recognize patterns. We recognize that for increasing emissions, there is an increase in temperature. We recognize that for an increase in temperature, there is an increase in the dynamics, let's say, people say there is an acceleration of some processes, meaning more turbulence, meaning that extremes may become more extreme. So the indication given by the models is indeed clear and very important. What we miss is some more details at the local scale. Because when we go at the local scale, uncertainty is still very relevant. So when we have to design an infrastructure, a local infrastructure, like a local water supply system, against climate change, against future climate, to be able to cope with future climate, this is a local intervention that needs a local prediction, which is still much uncertain. So we need to make progresses in this respect. At the global level, and you know that mitigation is a global strategy. At the global level, I think we have enough indications to support mitigation. At the local level, to support adaptation, still we need to move steps forward. Anyway, climate science and other sciences are working in that respect. We will probably never be able to completely eliminate uncertainty, but for sure, we will make progresses. Any question? Am I so clear? I doubt, but anyway, let's take it positive and let's say that if you don't have any question, it means that I am very clear. Okay, so let me move to one step forward. And I want to move forward with the next link, of course. Let me just close here. The next link is climate change and water cycle. Okay. Why climate change and water cycle? Because climate change affects the water cycle massively, intensively. There is a huge impact of climate change on water cycle. Water cycle means water resources, means rainfall, means floods, means droughts, means a lot of things that are very relevant to socioeconomic development. Indeed, the water cycle is an essential component of climate, as we mentioned. It's essential. On the other hand, there is to say that we usually consider water problems as local problems. So this is why sometimes when climate change is mentioned, water is not explicitly mentioned. I think the fact that the water problem is considered a local problem, it's a little bit misleading, because actually, for the importance of water at the global level, and for the global influence of local water problems, for the global extension of local water problems, I think it is a bit misleading to assume that water problems are a second priority with respect to global warming. This is what the communication channels tend to imply, that the major problem is global warming, and local problems like droughts, flooding, are important, but not as important. It is true that a local problem can be solved by local interventions. On the other hand, I think that if the water cycle gets compromised, the impact may be extended at the global level. What you can see here is quite a long lecture that in a way describes in some parts, there is some overlap with what we already discussed. But I want to focus on specific items which we didn't discuss yet. First of all, the lecture starts with an explanation of the greenhouse effect, which I think we can skip. And it is something that I think we already know. What is the dynamics of the greenhouse effect? The only thing that I want to reiterate is that CO2 is not the only one greenhouse gas. There are several greenhouse gases in the atmosphere, including methane, including water vapor, and water vapor, as you clearly understand, it's also naturally present like CO2, but the water vapor plays really an essential role in determining the greenhouse gas effect. Of course, the CO2 is the greenhouse gas that is increased more in the past decades. Okay, so this is why we often mention CO2, because it results from the fossil fuels, and it's a greenhouse gas that is the one that is largely affected. It's the most affected by the human activity. And there is also here, okay, a picture of global warming, and there are some pictures about glaciality. Why these pictures? Because global warming, even if there are some discussions related to its magnitude, so the estimate of 1.3 could be with different sensors, and with satellite measurement is a little bit lower, is 1.1. So there might be some discussion on the digits of the global warming, but the global warming is a reality. And as we see from several pictures here, there is an example of glaciers that are retreating, and it's clear. And then these are graphs of the progress of global temperature. We already saw this. And then there is a discussion in this page on, just one second, let me check if I produced the PowerPoint. Yeah, let me get the PowerPoint, sorry. It's better because otherwise there is a lot of text scrolling on the screen. It's not a nice thing. This lecture gives to you also an overview of the past changes in climate. Here. There are a few figures trying to explain past changes in climate. So we are now in a cold period. As I mentioned to you, we are in the tail of a glaciation. And during the period represented here, look at the horizontal axis, it's millions of years ago. So this goes back more than 500 millions here. And the way we reconstructed this data is through ice falls mainly. And here you can see the sequence of glacial periods, which occurred several millions of years ago, and were interrupted by cold periods, hot periods during which we didn't have any ice over the caps, over the poles. And what you see in the extreme right is a current period, which is cold, but actually, if we zoom on the right, we would see that temperature started to increase in the last part of the graph. The last part, I mean the past 10,000, 11,000 years. And this was the top of the last glaciation, 11,000 years ago. So the next figures will zoom on that period and will show you that starting from the top of the glaciation, 11,000 years ago, the temperature started to increase. So now we are, as I said, in a glaciation which is the Quaternary glaciation. There are links in the webpage if you want to get more information on this glaciation. And usually we call it the Ice Age, but it's actually the last one. And our understanding is that in the past we had also more severe glaciations. And let's look then at the zoom of the past 1,000 years. So here the scale is different. The scale is more or less 500,000 years ago. So not 500 millions. There is one less zero. So the horizontal scale is extended up to 500,000, 500,000 years ago. And you see that even during this glaciation, during the Quaternary glaciation, we had some fluctuations in what? Top graph, temperature. And you see clearly here the rise in temperature in the past 11,000 years. And there was a sharp increase and then a quite stable situation. But again, it is not zoomed on the extreme right, because if it was zoomed, you would see an increase of 1 degree in the very tiny slice at the extreme right. Okay, you see that there is a lot of variability in the past. Let's say 5,000 years, up and down, up and down, up and down. Some of them are witnessed by oral traditions, and by documents, by monks. So a lot of variability, but on the extreme right, there has been the increase of global warming. So as I said, the top graph is temperature. So it's taken from the Vostok Station ice core for the past, as you can see from the caption, 420,000 years. This is public domain on Wikipedia. In the middle graph, there is CO2 concentration. And in the lower graph, dust concentration. So what can you see? What can we see here? First of all, there is synchronicity between CO2 and temperature. And this is a known result. With the increase of temperature, we have an increase of CO2 release from the sinks, and in particular from the oceans. So this is why they are basically evolving in the same manner. There is a lot of correlation. There is some correlation also with dust concentration, less evident because dust concentration results from volcanic eruptions. So we know that volcanic eruption, if they are a large scale phenomena, can cause a decrease in temperature. So what we would expect is that with an increase in dust, we have a lower temperature, but the correspondence is less clear. Keep in mind that we are uncertain in this data. So the correlation between temperature and CO2 raises the famous chicken and egg question. So is it the increase in temperature that stimulates the increase in CO2, or is the increase in CO2 that stimulates the increase in temperature? So there is a prevailing convincement that the CO2 followed in the past the increase in temperature. So temperature increased for another reason, and the CO2 increased after the increase in temperature, while in the recent past, it could be vice versa, the other way around. So if the increase in CO2 that is triggering, originating the increase in temperature. But this is a question that is to some extent still open. There has been recently contribution published on the Journal of the Royal Statistical Society of London, or London or UK, I don't remember. Anyway, an important journal, where the authors proved that with a refined and rigorous and complicated statistical analysis, that it looks like there is indeed, also in recent time, a delay of CO2 with respect to temperature. But this paper is highly controversial. There have been requests to the editor to withdraw the paper, and the paper was not withdrawn so far. So to give you an idea of the sensitivity of these discussions, because these discussions are related to the fact that to the attribution problem, to the question whether or not if the increase in CO2 today that is triggering the increase in temperature. I think, yeah, this is relevant, but still, from the point of view of scientists and the point of view of policy making and adaptation, it's not so relevant. And even for the point of view of mitigation, I mean, we have to find ways to mitigate this increase in temperature. And of course, the question is relevant. The attribution problem is relevant because it's conditioning a little bit the policies that we can activate, but not to a large extent, actually. So I don't think it is a question that is really important. What is interesting from a scientific point of view is to take into account that there is synchronicity between these two variables, and with the past data, with the ice cores, it's not so easy to determine the delay of one with respect to the other. It is anyway an interesting question, and I think that it is something that it's a nice question, and trying to better understand how the climate system works, trying to better understand for what reason. I go back. We had this glaciation in the past, and we have this current glaciation. It's extremely interesting. We still don't know the reason for ice ages. I just want to mention to you that if we got back to the situation of 11,000 years ago, which probably was not the worst glaciation in the history of Earth, but 11,000 years ago, we had the glaciers reaching Verona, reaching the flat areas of Italy. And we had a large part of Northern Europe covered by glaciers. So this would be really something demanding. And you will see also the other changes in other variables that we know that occurred. This would be really tough. I mean, warming is indeed dangerous and bringing a lot of risks, a lot of problems. But any change in climate, no matter if it is warming or if it is cooling, I mean, it's really a challenge for a socioeconomic point of view. It is also a challenge for natural systems, but natural systems, they survived in the past to huge changes. Look at this graph. And you don't see temperature in the scale because the vertical axis is concentration of isotopes of oxygen, which are related to temperature. We will inspect more the relation between isotopes and temperature in another lecture. So you can see the changes in temperature, but it is something like 10, 15 degrees, 11,000 years ago, 10, 15 degrees colder. So it is really something interesting to try to understand what happened. It's also interesting because, as I said, natural systems would survive, they survive, so they will survive, but the socioeconomic systems were not there during glaciation. So it's an interesting question to wonder how humans in the current level of development could cope with the glaciation. It's also interesting to wonder how humans could cope with an increase, a further increase in temperature of 2 degrees, which would be big change. Okay, now let's zoom over the short period. Look at the scale here. The scale here is the calendar year. So we go back not 400,000 years, but we go back 2,000. Okay. And what you see here is short-term variability and what is called the medieval warmer period around the year 1000, 1100. Before that, we had a relatively cold period. And in the medieval warmer period, we know these are reconstruction of past temperature, but we know that there was what is called a climate optimum, and which stimulated a period of prosperity. Historically, if you look at the history of humans, in warm periods there was prosperity. In a cold period there were problems because during the cold periods floods occurred and also droughts. It's especially in the past it was complicated. And in the medieval warm period, the temperature was larger than what we experienced up to 1850. And the difference was quite significant, was like 1 degree, more or less 1 degree. It depends on the reconstruction. You see that this is an ensemble of reconstructions, and there is some variability depending on the proxy data that you observe. And then what is called the little ice age followed, which induced an expansion of glaciers, an expansion of the areas that were covered by snow. In fact, we know that even in the Apennines, there were large areas permanently covered by snow. We have documents that were written and published by natural scientists documenting the presence of permanent snow in large areas of the Apennines. Starting from about 1750, temperatures started to increase again. And then, you know, the progress after the Industrial Revolution, because we have seen several graphs. So this is the recent progress of temperature. It looks like now we have a temperature that is much larger than the medieval warm period. Actually, we have records that were taken by monks and historical reports documenting that in the medieval world period, the extension of glaciers over the Alps was reduced with respect to today. And also they say that the extension of the woods, the altitudes of the forests in the Dolomites, in the Alps, was higher than today. And therefore, the question is stimulated if the temperature was also higher than today. We may explain these differences by uncertainty, because of course, if you look back, here you see the black line on the right is observations. When you look back in the past, before 1850, they are reconstructions, and the reconstruction cannot describe a very short-term variability. So if you have a period of 30 years that was particularly warm, the reconstructions may not be able to capture it. And another thing to say is that if the warm period was lasted for a long time, it may be that the forests had the time to climb the mountains. And today it's still a short time after we experienced global warming. So maybe that the forests didn't have so far enough time to climb the mountains. Maybe that these changes will come. For sure, let's say that even in the short past, not in the far past, in the close past, we have periods of warming and cooling. And no matter what is your zone over series of temperature, you'll notice up and downs. And these up and downs, the causes, the drivers of these up and downs are largely unknown. So, in the same way, we don't know if this medieval war period was global or was only local. And we don't know if it was warm only in Europe or if it was warm everywhere. Okay. Climate models, we can forget it. And this is a graph progress of precipitation. This is the distribution of precipitation for each month over the globe. And the question is whether this distribution of precipitation is influenced by climate change. We still don't know. And we don't see, this is annual rainfall, or sorry, it's millimeters per month, so it's monthly rainfall. And it's interesting to look at the scale, order of magnitude. And so you see the blue line, the blue color, the dark blue corresponds to 200 millimeters per month, which means something like 2,000 millimeters per year, 2,000 and 2 meters, 2 meters and a half. And of course, the larger precipitation in the equator, but also in the boreal zone, we have a large precipitation in the north of Europe, for instance. And this is basically monthly precipitation. We don't have a strong evidence of changes in precipitation at the monthly and annual time scale. It looks like climate models predict for the future a reduction in precipitation, but the observations so far don't confirm that. It looks like it is more or less stable. There are fluctuations, of course, but it's not clear whether there is a trend, a final trend. This series, I think I already showed it to you. It's the time series of precipitation in Bologna. It's interesting because it's annual rainfall, and you can see here, you don't see a clear trend. What you see is the presence in the past of long-term droughts, multi-year droughts, which didn't occur in the recent past. It's not clear whether climate change may have reduced the frequency of multi-year droughts. So what I mean to say here is while there is a clear trend in temperature, the trend in precipitation is still uncertain. As I said, climate models predict a decrease in precipitation, but to give you an order of magnitude, up to 2100 with RCP 8.5, business as usual, this predicted a reduction in precipitation in Bologna of about 10% at the annual scale. It means that we will pass from 700 millimeters per year to 630 millimeters per year. But this prediction is the prediction given in the worst scenario. If we look at the scenario that corresponds to the current mitigation policies, there is no change predicted in precipitation in Bologna, to give you an idea. This is changes in extreme precipitation. This is the study that I authored. The graph is a bit complicated to understand, but if you look at the upper left graph, it's easier to understand. This is increasing frequency of extreme events, extreme rainfall events, because in the past slide I talked about annual rainfall. This is daily rainfall extremes, meaning the events that trigger floods. And if you look at this graph, you see an increase in frequency, but this increase in frequency, it's about 10%. And let me see, you see the progress in the upper left graph. It starts from -3 and it ends at +7. So it's about 10% in frequency. It means that if you had a frequency of extreme event one every 10 years, now it would be 1.1 every 10 years. It's not really significant. And even if you look at the intensity of these extreme events, the intensity of extreme rainfall, the changes are not much significant. Another interesting story is the sea level rise. And again, look at the scale, the time scale on the horizontal axis. It goes back about 25,000 years ago. And look at the amount of sea level change during the last glaciation. Basically, starting from about 12,000 years ago, the sea level increased of 100 meters. I remember that in the past 150 years, we talked about a sea level rise of 30 centimeters. So you understand what the effect of a glaciation could be. It could cause a decrease in sea level of 100 meters. So you can understand the big change that would be given by such an event. The sea level rise is given partly by melting of glaciers and snow, and partly by thermal expansion, contraction, because with the increasing temperature, you get an increase in the volume of water into the seas and oceans. But what is really amazing here is the order of magnitude. It is indeed something impressive. And here we have another graph which says the same thing. 100, 120 meters of sea level rise in the past 11,000 years. And what you see in the bottom is a map of the Earth with a 6-meter sea level rise. Let's assume that the sea level rise increases of 6 meters, and in red you get the areas that would be flooded, which is quite interesting. I mean, if it was 6 meters, indeed, the areas that would be flooded are much extended, especially in some countries like Greece or Indonesia, which are not very high, you know. In Italy, it wouldn't be a large problem. but in some countries, but of course, this is for 6 meters. Now, this is the progress of sea level rise along the past 150 years, more or less, starting from 1880. And first, what you see here is the sea level change. It's about 20 plus something centimeters. What is a bit impressive here is some increase of the annual rate of sea level rise after 1990. But apart from that, and the increase is not astonishing, it's not like when you look at the graph of temperature. Apart from that, you see that it is quite constant, quite, I mean, the sea level rise, the trend is quite smooth. There are no big changes in the rate, in the annual rate of sea level rise, starting from 1900. And so this means that indeed the sea level started to increase well before global warming. And after global warming, the trend is not much increased. So somebody says that it's delayed. So maybe it comes later. But I mean, if we talk about warming of the ocean, this is delayed. So there might be indeed a thermal expansion that is delayed. The component due to thermal expansion may be delayed. The component due to glacier melting, I don't think it's reasonable to assume that it's delayed because it takes some time, of course, to the ocean topography to adapt, but not 30 years. So we would expect a larger increase of sea level rise due to global warming. On the other hand, there is much more that we still don't know. By the way, if you are interested in sea level rise and many other things related to climate, there is the website of Judith Carey. I just want to give you this invitation, and then we make the break. So let me open a Google page, Judith Carey. And she's a very famous climate scientist. There is a Wikipedia page, etc. And there is the website here of Judith Carey. There are a lot of reports, related to climate change. They are very interesting. I took some of the figures from these reports. And there is to say that in the global debate, in the global climate debate, Judith Carey is more on the part of natural variability than human influence. Just to give you an idea, you know that there is this debate that whether or not climate change is due to anthropogenic effects. And the vast majority of people are convinced that humans play an important role. Judith Carey is a little bit more in the middle. She recognizes that there is a human influence, but she also points out that there is a lot of natural variability. And she basically, this graph, I think it was taken from her report, and she used this graph in order to demonstrate that the sea level rise is not completely disjointed. It's not completely associated to global warming, but there is some dynamics that is natural and it's not fully understood. I think we can make a break now. Do you have any questions before we stop? Okay, let's reconvene at 4:31. Thank you. Okay. I assume you don't have any questions, so let's move forward. And here is another graph of sea level rise during the past 30 years. Basically, it doesn't deliver any additional information. And what is interesting is to look at the text, which is taken from the fifth assessment report of the IPCC. And I am reading, it's a quote: "It is very likely that the mean rate of global average sea level rise was 1.7, from 1.5 to 1.9. The range is given to uncertainty. Millimeters per year between 1901 and 2010, and 3.2, 2.8 to 3.6 millimeter per year between 1993 and 2010. It is likely that similarly high rates occurred between 1920 and 1950. So basically what they say is that we observe cyclical behaviors also in sea level rise. There is indeed some increase, some slight increase in the past, during the period of, during the global warming period. And but there were similar trends also in the past. This gives an idea of the level of our understanding, which is still subjected to a lot of uncertainty. If we look at satellite measurements of global sea level, we see some differences in measure. Basically, this is due to the fact that the different sensors give different trends, and there is, I think, the difference is not very significant. And but let's consider that satellite measurements of sea level started in the 1990s, so only recently. And what is, I think this slide is takes our attention, is relevant because it talks about predictions. These are predictions given by the fifth assessment report. I am not sure predictions of sea level rise have been already published for the sixth assessment report, which is being published during this month. They started last year, and I'm not sure they are already published. In any case, I think that looking at the prediction of AR5, it's not they are not outdated. It's not inappropriate. And it is interesting to look at the order of magnitude. So predictions are given for two time slices, 2046, 2065, and 2081, 2100. And they are given for the different scenarios. And it's AR5, so they are given for the RCP scenarios. They are very similar to the SSPs anyway. Business as usual, I remind you, is 8.5, RCP 8.5. And the predictions are given in terms of mean and likely range. Again, likely range to account for uncertainty. And these are predictions of global mean change in temperature and global mean sea level rise. So if we look at the period, at the last period, where we expect to find the largest changes, we see that under the business as usual, the most pessimistic 8.5, the predicted change in temperature is 3.7 on average, and 2.6 to 4.3 is the range. This is warming with respect to the pre-industrial period. So 3.7 means that with respect to now is more or less 2.5 degrees more which is beyond the Paris target, the target of the Paris Agreement, and beyond, of course, the +2 target. The target of the Paris Agreement is +1.5. If we look at the corresponding sea level rise, it's about 0.63 centimeters, with a likely range between 0.45 to 0.82. Keep in mind that we already have like some 22 centimeters of sea level rise already, so it's about plus 40 centimeters more. It is not a huge increase. You may remember the map of the flooded areas corresponding to a sea level rise of 6 meters. So this is much lower than that. And and it is relevant because when we talk of 40 centimeters more in terms of saltwater intrusion, in terms of coastal flooding and under extremes, it's still a relevant measure. But it is not, I mean, it is not the reason of a major concern. On the other hand, keep in mind that what I said about the tipping points some time ago, a couple of weeks ago. These models cannot predict the possible existence of tipping points in the melting of the ice caps. It may happen that the ice caps suddenly melt, suddenly are melted because of the rupture, for instance, of the outburst from hidden lakes that are incorporated into the ice, or other reasons. So we don't know in the past when the ice cap melted, if the melting was quick or slow and associated to a linear correlation with the increase in temperature, without tipping point, without threshold, we don't know. So these predictions are subjected to uncertainty that goes beyond the range that is indicated in the table. What is their meaning then? Their meaning is that under the assumptions that correspond to our current knowledge, this is what we may expect. It is a useful indication, but on the other hand, let's not forget that the Earth system, the natural systems are known also to be affected by tipping points, which may cause an abrupt change. Sorry. Now let's talk about flooding. And what you can see here is a graph of the maximum annual discharge, peak flow of the Po River. It is taken from daily data. And actually, this is supposed to be an animated figure, but I see that, okay, now it's animated. And you can see also there a regression line that moves along the graph. The regression line is computed on a window that is 50 years long. It's quite a long window. It's a huge temporal scale. So the slope of the linear regression is reliable. And what you can see is that there is a lot of variability. If we draw a regression line along the full extension of the series, we will find a slightly increasing trend in annual river flow, but in the maximum annual flow. Here you can see that it's progress is again subjected to uncertainty. If we look at the large floods, we see that in the period we had 4 large floods. One was in 1929, I think, and another one soon after, I think it was a couple of years later. One in 1951 with the breach in the Livii that flooded the area around Occhiobello, around Ferrara. And then we had the 2 floods in 1994 and 2000 with no inundations because the levees resisted, but we were very close to get an inundation, especially in the year 2000. After 2000, we didn't get any major flood in the Po River And it is a relevant question to wonder whether or not the frequency of this type of floods is increasing. This is an example, the floods of the Po River are an example of large-scale floods because the Po River is extended over several regions and therefore the flood is caused by a very extended rainfall because if the rainfall is very local, the Po River is not sensitive. The Po River is sensitive to rainfall events that cover the whole catchment, the whole Po River basin, which includes the regions of Lombardia, Piemonte, part of the Veneto region, and part of Veneto region is just very, no, I don't think it is relevant. It's Piemonte, Lombardia, part of the Liguria, and part of the Emilia-Romagna, of course. And therefore, I mean, we need a very extended rainfall in order to cover it. So these are, again, large-scale floods. It is more challenging the question whether small-scale floods are influenced, but let's wait before replying to this question. Because a large-scale study of recent changes in flood peaks in Europe was recently performed. These are, again, quite large-scale floods. And what they found is that the pattern is not homogeneous. In some part of Europe, we noticed an increase in the frequency and also an increase in flood peaks. In other parts of Europe, a decrease. What they found with this study, first, let's say these are large-scale floods, but the scale is reduced with respect to the scale of the Po River. Second, what they found is that where the snow melt is a significant driver of flooding, then a change was detected. Because the idea is that global warming is affecting snow melt, and therefore it's affecting the magnitude of floods, especially the floods that are due to snowmelt or to rain on snow. This is a risky driver. When you get snow and then soon after rain over snow, you have a sudden melting of the snow causing an increase, a huge increase of river flow. It's like a tipping point. Even a small amount of liquid precipitation over a huge amount of snow can cause a rain on snow effect. And where these phenomena are relevant, are important drivers, they found an increase in the frequency of floods. This is another abstract extract from this contribution. What is important to say, this contribution and another one, what is important to say is that also they found a change in seasonality. So the timing of high flow was anticipated. So change in seasonality for the same effect of anticipated snowmelt. So where snowmelt contribution is important, the change in seasonality was found to be as well important. Another interesting figure and concept, El Niño. So, do you know what El Niño is? El Niño is an index that is computed based on the difference in temperature in the West and the East Pacific Ocean. So it is measured the temperature of the Pacific Ocean close to Australia, the temperature of the Pacific Ocean close to South America, and then based on this difference in temperature, El Niño is expressed why the difference in temperature? What you see here, it's west on the left. It's a diagram of the Pacific Ocean, okay? And you have left on the west on the left and east on the right. So it's on the right, you have South America, the west coast of South America, and on the left, you have the east coast of Australia. So if you get warm over Australia and cool over South America, you have basically a circulation of water into the ocean that follows the circle that you see depicted. So you have current in the bottom of the ocean moving water from left to right, and currents in the upper part of the ocean moving right to left. And this is El Niño, okay? And what happens is that, just 1 second, I get to the web page because I think there is another figure that is relevant. Okay. Okay, here it is. Sorry, this is La Nina, I forgot. And the opposite is El Nino. This is La Nina. And let's look at here. Because I think there is a similar diagram for El Nino. Okay, okay, it's not in English, but we can read this, it's no problem. You see the two opposite situations. So there is La Nina on the left and Nino on the right. And you see what is the effect in terms of distribution of climate. Okay. El Nino brings rainfall over South America, and so possible flooding, and droughts in Australia, and the opposite for La Nina. And this is due to the fact that when you have this circulation of water, there is an effect of this movement of warm water masses, which causes larger evaporation and therefore precipitation in correspondence of the warm water. And then you have, which is also favored the precipitation by the circulation of cold air that is stimulated by the difference in temperature of the ocean, which causes, once again, precipitation in correspondence of the warm part. Now, the effect is not limited to Australia and South America. The effect is also extended over the North of America. So California, droughts in California and Canada are heavily influenced by El Niño and La Nina. El Niño and La Nina is the result of ocean circulation. It's the result of a climatic input, because the warming of the ocean or the cooling of the ocean is caused by the local climate. What is relevant is that this situation lasts for a long time. So once that there has been this discrepancy in temperature has been activated, it lasts for a long time. So these indexes of global circulation in the oceans and the atmosphere are highly effective on climate. So we know that, for instance, persistent droughts in South America are related to the occurrence of La Nina, or persistent flooding in South America are influenced by El Nino. Two research questions here. Is it possible to predict El Nino and La Nina? Reply so far is no. We know that they are cyclically varying, but there is no fixed periodicity. We cannot make a prediction in advance. Second question, are El Nino or La Nina influenced by global warming? Up to now, we don't know. It looks like they are not, because their occurrence, basically the frequency of this phenomena, don't look much changed after global warming. But it is an open question. So I think this is an interesting digression on the physics of global climate, which is influenced by large-scale circulation patterns. Some of these are called atmospheric rivers. These are perturbations, movement of water in the atmosphere, which cause large-scale phenomena. When we talk about atmospheric rivers, we talk about flooding, of course, and these are extremely relevant. We can really relate climate to these circulations, but still we cannot predict the dynamics of these circulations in the long term. We can predict them at the meteorological scale, 1 week, couple of weeks, and this is how meteorological predictions are derived, but still in the long term, we cannot make a prediction, and we don't know if these global circulation patterns are affected by climate change. Okay, El Nino, here you see some consideration, typically occurs every 2 to 7 years. And the El Nino that occurred in 2015 and 2016 was called a Super El Nino, the worst in 15 years. And the two previous Super El Ninos occurred in 1982 and 1997. And here there is a textual description of the phenomena. Okay. Now let's talk about droughts. This is again a graph of the Po River, but now we depict the minimum annual water discharge. And again, a regression line. So if you draw a regression line through the full extension of the graph, you get a slight decrease in the minimum. And but if you draw a regression line, a moving regression line, you see periodicity. This was completed by several recent studies, because here you see the graph is extended to 2009. Actually, if you look at the low flows of the Po River at the monthly time scale, typically in July, because typically is the minimum, July, sometimes August, we found recently that starting from 1807, we have measurements, 6 of the 10 worst droughts occurred after 2000. So it is clear that there is an increase in drought frequency. The magnitude of the drought, it is drought that occurred in 2022 is the worst one, but the other droughts compared with those that occurred in the past are not really worse, but the frequency is for sure increased. And what is the reason? What was found is that the reason is again snowmelt, anticipated snowmelt, because actually there is an increase in the spring river flows and a decrease in the summer river flows. So it's due to anticipated snowmelt. In general, the frequency of drought, it is an open question whether or not it is affected by climate change. Of course, the feeling is that it is, because you know, with warming, there is increased evaporation and there is an increase in water demands. So the feeling is that indeed the global warming exacerbates, aggravates the risk of drought. but this is something that is still under investigation, because if we look at the distribution of annual rainfall, we don't see big changes. And if we look at the distribution of minimum rainfall in the driest month, it's not much changed. So are droughts, is the frequency of drought increased after global warming? It's an open question. Climate models predict an increase in drought frequency and intensity only for some regions. For instance, if we look at Italy, climate models don't predict a huge increase in drought frequency. Droughts are a relevant risk, and of course we are more impressed by flooding, because flooding is a sudden event. Flooding is causing sudden death and sudden damage, and also, you know, floods require a huge intervention for recovery. And for droughts, they look maybe they are slower, their evolution is slower, so they don't take us really by surprise. We have time to get prepared, we have time to manage, but still, they are a very relevant risk, especially in some countries. If we look at the global damages caused by droughts and floods, they are comparable. So, I mean, it is indeed a relevant risk, and whether or not they are influenced by climate change, it's for this region a compelling question. Here I quote some studies where it is concluded what I just summarized, and it is interesting to read the quote here by Brown and others in 2012, a scientific paper. A problem with this approach is that GCM projections are relatively poor scenario generators. They describe a lower bound on the maximum range of uncertainty. Even a large multimodal ensemble provides relatively few samples in a typical analysis related to the size possible through stochastically generated risk analysis. Larger ensembles are becoming available, such as via the climate prediction experiment or the coupled model intercomparison project, but still face issues of biases that may preclude the discovery of plausible climate risks. And this is referred in particular to droughts. We already discussed the projections, and let me see here. This is a slide that is referred to strategies and policies for climate change mitigation. Besides the storage of, the reduction of CO2 emissions, there are some techniques known as also geoengineering, which basically are based on capturing CO2 in the atmosphere, artificially capturing through membranes, for instance, through filtering, or natural capturing through increasing the surface of forests. And this is a way to capture CO2 from the atmosphere and injecting CO2 into the ground through forests. We can do that because clearly the carbon captured by the vegetation is then given back to the ground through the degradation of the organic matter, or we can make an artificial injection. What we do usually is to use depleted oil reservoirs or gas reservoirs and inject CO2 in the ground. The hope is that in this way we can restore the original carbon sinks, the original carbon reservoirs. So we take oil from the soil and we inject CO2. And the idea is that in the long term, you get a recovery of the oil reservoirs. Actually, it's not yet clear if this technique works. It is practiced in the United States. There are a lot of investments in carbon injection, and it's CO2 that is captured directly from the atmosphere or captured directly from the sources of CO2 that is then re-injected into the ground. But you know, one thing is the natural process of carbon storage that passes through several natural steps. And another thing is the direct injection of a gas. So for instance, one of the questions is related to the possible leakage of the CO2 that is injected in the ground and then leaks back to the surface and back to the atmosphere, because the natural process is not gas injection. The natural process is carbon storage through organic matters that is then degraded in the underground. There is a production of gas also, but the production of gas occurs only in some places. So it's not clear whether part of the injected CO2 then comes back through leakage. But these are techniques that are largely used in the United States. In Europe, they are still not much applied. And you see capture and separation through membranes, and then we can have storage injection in geological formations. Okay, now this is part of a mitigation strategy. And in the website, there is a description of several different mitigation strategies. Let me just check where we are here. And emission reductions mitigation through emission reduction, and also increasing carbon sinks. Okay. You know, it is a costly procedure. So the doubt is that if this technique is not going to be effective, this is, of course, absorbing resources that could be dedicated to other mitigation policies for adaptation. Unfortunately, the presence of uncertainty makes everything a bit uncertain as well. Okay, the effectiveness of these procedures, I mean. Now, let's mention a few words about adaptation. We already discussed adaptation a little bit. And what is interesting here is the list of possible adaptation policies, so, which is here. Let me see if I have it in the slide. It makes it more, yeah. Okay, so let's try to comment very quickly each one of these. So protective and or resilient technologies and materials that are prone, in properties that are prone to flooding, flood-proof buildings. This is one possible adaptation option, very local. Changing to heat-tolerant tree varieties. So it means that in order to protect the vegetation and the beneficial effect of vegetation, we change the vegetation cover to heat-tolerant species. Rainwater storage to deal with more frequent flooding in urban areas. Changing to water-permeable pavement, like parking areas. Adding water buffering vegetation, greening urban areas in order to reduce the water flow in the sewer systems. Adding underground storage tanks to sewer systems, and subsidizing household rain barrels, which means storing rainwater at the house level, reducing paved areas to deal with rainwater and heat in urban areas, adding green roofs and green walls to deal with rainwater and heat, requiring waterfront properties to have higher foundations in order to avoid that water bypasses the foundations and gets into the properties, raising palm and wastewater treatment plants, and surveying local vulnerabilities, raising public awareness, and making climate change specific planning tools like future flood maps, incentivizing lighter colored roofs to reduce the heat-island effect, installing devices to prevent seawater from backflowing into storm drains, because this is a huge issue, because then you get salinity into the rainwater, and installing better flood defenses such as seawalls and increased pumping capacity, buying out homeowners in flood-prone areas. This is called also delocalization. It is nice to say, but unfortunately, we need economic resources to buy out the homeowners, and we need also a kind of socio-economic capacity to carry out, to apply these techniques, and raising the street level to prevent flooding. Climate change mitigation and adaptation is, of course, a very relevant issue today. Okay, so I think we are done, and there is actually an addendum here, which basically says that a relevant question is the design of these systems. So I made a list of solutions. These solutions need to be designed, need to be sized. And the relevant question is, what kind of future climate should I get prepared to cope with? And this goes back to the issue of prediction, generating future climate scenarios. There is no technical indication. There is no suggested procedure for inferring, estimating the design variables, so the features of future climate. So what kind of extreme rainfall should I cope with in the future? There is no codified answer to this question. And let me also add, some of the solutions that I mentioned are part of the so-called nature-based solutions. So greening roofs, greening walls, and restoring vegetation in urban areas. What is the effect? If we need to make a design, if we need to devise a strategy, we have to estimate the effects in terms of adaptation, of mitigation of the consequences of climate change. And there is no guideline to estimate the contribution given by nature-based solutions. Today, we move forward with experiments. So in an urban area, we try to green a part of the urban area and see what happens. In terms of temperature, for instance, what is the contribution to cooling during summer? And then after the experiments, which need to be carried out at the local level, we draw conclusions that are very local and cannot be easily extended. Okay, any question? Yeah? Okay, so mitigation is the way try to reduce climate change. And the way that we follow is by reducing the CO2 concentration in the atmosphere. Adaptation means that we accept climate change and adapt to it. So we accept flooding, and I make my home flood-proof. Yes, adaptation means that we give up to fight global warming and we adapt to the consequences, which is the usual way of humans to cope with climate variability. They try to adapt. And of course, today we have the knowledge that supposedly may allow us to change climate. And for instance, by reducing CO2 emissions. Any other question? Thank you for your question. Okay, I think we are done. Thanks a lot. See you next Monday, same room. Grazie. Grazie anche agli interpreti. Grazie mille.
Grazie, grazie mille. Grazie.
Grazie.
Alla prossima.
Alla
Sì.
prossima.
Una domanda sul programma, la lezione